Hi everyone, what's up? Welcome back to my tutorial channel. Daniel's here and today I'm gonna finish my topic 3, numerical summaries or descriptive statistics in the series of elementary statistics. And the lesson today is about measures of position, including Z-score, quartiles, percentiles, five number summaries, outliers, and Boxplots. So first let's get started off with Z-score. What is a Z-score? Let X be a value from a population with mean mu and standard deviation sigma. The Z-score of X is Z is equal to X minus mu over sigma. For example, a National Center for Health Statistics study states that the mean height for adult men in the United States is mu is equal to 69.4 inches, with a standard deviation of sigma is 3.1 inches. The mean height for adult women is mu is equal to 63.8 inches, with a standard deviation of sigma is 2.8 inches. Who is taller relative to their gender? A man 73 inches tall and a woman 68 inches tall. So here in this situation, we cannot compare the height of a man with a woman by simply using their actual heights. And in this situation, we need a tool that is the Z-score. Z-score is just like a common tool to compare two values from different population. So here I'm gonna find the Z-score for a man 73 inches tall and a Z-score for a woman 68 inches tall. The Z-score for a man 73 inches tall is Z is equal to 73 minus 69.4 over 3.1. 73 is his actual height. 69.4 is the mean of his population, and 3.1 is the standard deviation of his population. And we got the first Z-score is 1.16. Now similarly, we find the Z-score of a woman 68 inches tall. Z is equal to 68 minus 63.8 over 2.8. 68 is her actual height. 63.8 is her population mean height, and 2.8 is the standard deviation of her population. And the Z-score for her actual height is 1.5. So now it turns out that a woman 68 inches tall is actually taller than a man 73 inches tall because her Z-score is way more higher than his Z-score. So in this case, the woman is actually taller than the man. So in short, Z-score is a tool to compare two data value from different population using different measurement. That's the application for Z-score. Now we are going to combine the Z-score and the empirical rule. Remember in the last lesson when I introduced empirical rule, when a population has a histogram that is approximately bell-shaped and symmetric, the empirical rule is applied as follows. Approximately 68% of data will be within one standard deviation. Approximately 95% of the data will be within two standard deviation, and all or almost all of the data will be within 3 standard deviation. So in the lesson today, we combine the empirical rules with the Z-score. Within one standard deviation, that means between negative sigma and sigma. And the Z-score for negative sigma is -1. The Z-score for sigma is 1 because sigma minus minus 0 over sigma is -1, and sigma minus 0 over sigma is 1. So combine the empirical rule with Z-score, we have approximately 68% of the data will have Z-scores between -1 and 1. Similarly, we apply the empirical rule for the and Z-score for the last two statements. The Z-score for -2 sigma is -2. The Z-score for 2 sigma is 2. So Approximately 95% of the data will have z-score between nib2 and 2. And the last one is simple. All or almost all of the data will have z-score between nib3 and 3. Example, in a recent survey of 655 working Americans ages 25 to 34, the average weekly amount spent on lunch was 44.60 with innovation of 2.81. The weekly amount are approximately bell-shaped. Estimate the percentage of amounts that are between 41.79 and 47.41. So here, the mean of the population is 44.60 and the innovation is 2.81. The question asks for the percentage between two numbers 41.79 and 47.41. One thing we notice here, the z-score for 41.79 is 41.79 minus 44.60 over 2.81, we got -1. And the z-score for 47.41 is 47.41 minus 44.60 over 2.81, and we got 1. So the percentage of amount that are between 41 and 79 and 47.41 is basically the percentage of data that have z-score between -1 and 1. So apply the empirical rule. Approximately 68% of the data will be having the z-score between -1 and 1. Next, quartiles. What is quartiles? The definition is every dataset has 3 quartiles. The first quartile, denoted by Q1, separates the lowest 25% of the data from the highest 75%. The second quartile, denoted by Q2 or also median, separates the lower 50% of the data from the upper 50%. So Q2 here is basically to the median. The third quartile, denoted by Q3, separates the lowest 75% of the data from the highest 25%. Example, here's the procedure for computing the quartiles. The first step, we need to arrange the data in increasing order because order here does matter. So we need to arrange the data in increasing order. Step 2, let n be the number of values in the dataset. To find the first quartile, we compute L. L is 0.25 times n. And for the third quartile, compute L is 0.75 n. For the median, we have already learned how to find median from the last lesson of measure of central tendency. Step 3, if L is a whole number, the quartile is the average of the number in position L and the number in position L plus 1. If L is a whole number, round it up to the next higher whole number. The quartile is the number in the position corresponding to the rounded up value. Example, find the first quartile Q1, the median M, and the third quartile Q3 of this dataset. So just follow the procedure to compute the quartiles. First, we need to rearrange the dataset in increasing order. Then we are going to compute the L number. For the first quartile Q1, L is 0.25 n. N here is 26, so we got 6.5 is the L number for Q1. Similarly, we have Q3, the L number is 19.5. Step 3, now we look at the L numbers. For Q1, 6.5 is not a whole number, so we need to round it up to the higher nearest number, which is 7. So the first quartile is the number that is at position number 7 on the increasing order dataset. So we start counting 1, 2, 3, 4, 5, 6, 7. So the first quartile of this data set is 3. For Q3, L is 19.5, which is not a whole number. So we need to round up to the higher nearest whole number, which is 20. And then we start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 16, 17, 18, and 19, 20. So Q3 is 7. And for the median, remember from the last lesson we have learned how to find the median. Here we have 26 numbers, so the median is the average of number at position 13 and 14. So we have 4 plus 4 divided by 2 is 4. So the 3 quartiles of this data set are 3, 4, and 7. Next, percentiles. For a number p between 1 and 99, the p percentile separates the lowest p% of the data from the highest hundredths minus p%. The procedure for computing the p percentile is the first step we rearrange the data in increasing order. Step 2, let n be the number of values in the dataset. So for the p percentile, compute the value L is p divided by 100 times n. If L is a whole number, then p percentile is the average of the number in position L and the number in position L plus 1. If L is not a whole number, then round up to the next higher whole number. The p percentile is the number in the position corresponding to the rounded up value. And we have the reverse problem. So for the last problem, we are given the p value and we was asked to find the p percentile. Now in the reverse problem, we need to compute the percentile corresponding to the given data. So to do so, the first step, we also have to rearrange the data in increasing order. Step 2, let's X be the data value whose percentile is to be computed. Use the following formula to compute a percentile. The percentile is 100 times number of value less than x plus 0.5 over number of values in the dataset, and then route the result to the nearest whole number. Example, given the datasets 41, 42, 42, 44, 44, 45, 45, 46, 49, 49, 51, 51, 53, 56, 57, 59, 59, 63, 67, 71, 77, and 100. This dataset is already in increasing order, so we don't need to do the first step because this dataset is already set. Now, what is the percentile corresponding to 51? So 51 is right here. We have two numbers, 51. And the question asks for the percentile corresponding to 51. So here we see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 number that is less than 51. So the percentile of 51 is 100 times with 10 plus 0.5 over 22, and we got 47.7. So 51 is the 48th percentile of this dataset. Next, the 5-number summary. Definition: the 5-number summaries of a dataset consists of the following quantities: minimum, first quartile, median, third quartile, and maximum. Example: here is a table that presents the number of students absent in a middle school. We got 65, 67, 71, 57, 51, 49, 44, 41, 59, 49, 42, 56, 45, 77, 44, 42, 45, 46, 100, 59, 53, and 51. So to construct the 5-number summaries, we need to find the minimum, the first quartile, or the median, the third quartile, and the maximum. To find the fourth quartile and median and third quartile, we need to rearrange the dataset in increasing order. So first step, just rearrange the dataset. Here we see that the minimum is 41, the maximum is 100. And the third quartile here is 45, the median is 51, and the third quartile 59. In this five number summary slide, I don't show you in detail how to find the fourth quartile, median, and third quartile because I have already shown you from the previous slide. So the five number summary for this dataset is 41, 45, 51, 59, and 100. Next, outliers. An outlier is a value that is considerably larger or considerably smaller than most of the values in a dataset. Some outliers result from errors. For example, a misplaced decimal point may cause a number to be much larger or smaller than the other values in the dataset. Some outliers are correct values and simply reflect the fact that the population contains some extreme values. For example, the temperature in a downtown location in a certain city is measured for 8 consecutive days during the summer. The readings in degrees Fahrenheit are 81.2, 85.6, 89.3, 91.0, 93.2, 8.45, 79.5, and 87.9. Here you see that there is a ridiculous number 8.45, which is different from the others. So 8.45 is an outlier. So the outlier is 8.45, which is much smaller than the rest of the data. This outlier is certainly an error. That could be the case that the decimal point was misplaced. So there should be 84.5, but we misplaced the decimal. So in this case, the outlier should be corrected if possible. If we cannot correct it, then we have to delete it. But in this case, I suggest you to just correct us 84.5 to 8.45 to 84.5. Interquartile range IQR. The interquartile range is found by subtracting the first quartile from the third quartile. IQR is Q3 minus Q1. This is very simple. The IQR methods for finding outliers. So the last slide, I show you how to detect outliers. However, it's just by your institution. Here I'm going to show you a correct method to detect the outliers using IQR. The first step, we find the first quartile and the third quartile, Q1 and Q3. Step 2, we compute the interquartile range, IQR. We subtract Q1 from Q3. Step 3, we compute the outlier boundaries. These boundaries are the cutoff points for the determining outliers. The lower outlier boundaries is computed as Q1 minus 1.5 IQR, and the upper outlier boundary is Q3 plus 1.5 IQR. So any data value that is less than the lower outlier or greater than the upper outlier boundary is considered to be an outlier. So that's how we use IQR method to find outlier. And the last thing today I would like to talk about is Boxplot. A Boxplot is a graph that presents the five number summary along with some additional information about a dataset. There are several kinds of Boxplots. The one we describe here is sometimes called the modified Boxplot. So here's the modified Boxplot, and on the modified Boxplot, we have Q1 is reference the first edge of the box. Then we have the median, we have Q3, and there's a line starts from the lower outlier boundary and finish at the upper outlier boundary. This is a modified box plot. For the common box plot, many people draw the whiskey line from the minimum to the maximum instead of from the lower outlier boundary to the upper outlier boundaries. So to construct a box plot, first we need to find Q1, median, Q3, the lower outlier boundaries, the upper outlier boundary, and then we make the horizontal line and mark the value of the dataset on the horizontal line. Then we draw a vertical line at the Q1, another vertical line at median, and another vertical line at Q3, then finish the box. The last step is draw the whisker line, that is a horizontal line, start at the lower outlier boundary and finish at the upper outlier boundary. And make sure this line is lie at the middle of the box plot. So that's how we construct a box plot. Now we learn how to determine skewness from a box plot. Just like histogram have three common shapes: right skewed, left skewed, and symmetric. The box plot also can show you the skewed dataset, the symmetric dataset. So here is an example of the datasets that the histogram is skewed to the right. So in this case, if the median is closer to the third quartile, this is the median. In this case, you see the distance between Q1 and the median is smaller than the distance between the median and Q3. So in this case, the median is closer to the third quartile than the third quartile, or the upper whisker is longer than the longer whisker. The upper whisker is this line. It's much longer than the whisker, the lower whisker. So in this case, we say the data are skewed to the right. The opposite of right skew is left skew. So this is an example of left skew data. You see that the median here is pretty much closer to the third quartile than the fourth quartile, and the lower whisker is longer than the upper whisker. So this is an example of the data that is skewed to the left. And the last case is symmetric. If the median is approximately halfway between the third and the third quartiles, you see that the median here is at the middle, and the two whiskers are approximately equal in length. The lower whisker and the upper whisker is almost equal. The data are approximately symmetric. So that's how we use Boxplot to determine the shape of the histogram and determine the tendency of the data. So that's everything for today. Thank you so much for watching my video. I hope you guys enjoy my video and see you next time. Bye.